Hello class, this video here is exclusively for section 5.3 in your text. If you remember, we said we were going to backtrack from chapter 6. We'll do 3 sections here in chapter 5, and then we'll jump ahead to do 3 sections in chapter 7, and that's where we'll finish everything up. But before we do, let's lead in a little bit to chapter or section 5.3 right here. Notice we have on the screen already a right triangle with the angle theta already indicated. Okay, right here. And let me make sure this isn't going to delete. Okay. So, of course, the side that would be opposite right here, that's the opposite side of theta. This is the adjacent side of theta, and the side always opposite the right angle is your hypotenuse. Let's go ahead and place this triangle on a coordinate plane where the vertex here of the angle theta will be the origin. So let's see if I can line it up real good. There's our y-axis. And there is our x-axis. Okay. Label them accordingly. There we go. All right. Now, next thing I want to do, I'm going to place a circle on this xy plane where the center of the circle is right there at the origin, which also happens to be the vertex of the right triangle there where the angle theta is. So let's put a circle there. All right. So next thing I'm going to do, I'm going to take another line segment here and drop it down right from this point where the triangle and the circle, oh, I'm still on a circle, let me delete that. Choose that tool. Drop a little line segment down right there. And you'll see that we have another right angle here. And what you'll notice is what we've created are similar triangles, okay? Now, I didn't label anything, but let's just say this was triangle A, B, C, and maybe here we have A, B prime, C prime. Those two triangles, the big right triangle, okay, and the small right triangle would be similar to each other. And what that means is, in similar triangles, if you remember from your geometry days, corresponding sides of the triangles are in proportion to each other, like a scale. Think about when you're drawing a scale model of let's say, a stadium that's to be built. And maybe you draw the model, or you create the model at maybe 1/100th of the size. So whatever the size of your model is, if everything increases by a factor of 100, then you have the real stadium. Trees, cars, people, the stadium itself, the signs, everything. All right. So when you have that, you can make certain, sorry, I think I lost my audio there for a second. You can make certain conclusions or come to certain conclusions about the sides of those triangles in reference to the angle theta. Now notice the angle theta is pretty much sitting in the same exact spot for both the bigger triangle and the smaller similar triangle inside. Okay? Because the definition of let's say the sine is the opposite side over the hypotenuse, okay? No matter what, if you look at, say, the bigger triangle, here's the opposite side here, and here's the bigger hypotenuse, okay? For the smaller triangle inside, here's the opposite side, here's the hypotenuse. Now, again, those sides are in proportion to each other. They're obviously not congruent. They're not the same, but they both have the same angle. So remember, the sine function and the cosine function, all 6 functions are ratios. Okay, they're ratios. So this angle measure is exactly the same for both the bigger and the smaller right triangle. If the angle measure is the same, and we can see that just by inspection, then the ratios of the opposite sides of the hypotenuse for both have to be equal to each other. Okay? So we can make that presumption. Let's say, I'll give these sides some lengths. Let's say, let me see. What I'm going to do is, just so you guys can see exactly what I'm pointing to here, I'm going to just mark off this little arc, purple here. I'll give it a label. We call that arc T. Okay? So again, last week we began referring to the opposite side, the adjacent side, and the hypotenuse in terms of three letters. Okay? R, X, and Y. The opposite side is Y. Okay? The adjacent side is X, and the hypotenuse is R. Now, we are dealing with a single unit here. Call it the unit circle. And remember what we talked about the radius always being positive? Well, because it's a distance, we're going to let the radius be 1. All right, we're going to let the radius equal 1. And if the opposite side is still y, and the adjacent side is still x, like we spoke about in class, okay, then we can define the sine of this angle as the opposite side, y, over the hypotenuse, 1. And y over 1 would just be y. If we wanted to look at the cosine of this angle, we know that the cosine is defined as the adjacent side, in this case, x, over the hypotenuse, which we're going to let be 1, so it's x over 1, or just x. Okay? Now, also remember we talked about when we are looking at radians. So let's assume that this angle is being measured in radians. Now, it's not perfect. It would be a little bit bigger if it were. But remember when we talked about a radian, 1 radian was when that the radius is equivalent to the arc length. Okay, now of course it doesn't appear to be that way. That's why I'm using the little disclaimer that it's not drawn to scale. Okay, but let's make that assumption. If that's the case, then what we can then go further on to say is that the angle and the arc that's being cut off by the sides of this triangle here, okay, by the 2 radii coming out, they must be equal to each other. So we could take out the theta if we want and substitute in the t and still have equivalent statements. Okay? All right, so that's just a little setup of what we're talking about. By the way, this we could say more explicitly. All right, this is point x comma y right here. This is the point x comma y right there. Okay, for angle theta. Again, the radius would be 1 in this particular case. And you know, this is where we lead up to the unit circle a little bit in our discussion. All right, so I wanted to give that to you as a kind of a lead-in because what we're doing now is we're going to start looking at the graphs of the sine and the cosine functions. So what I'm going to do, let me clear everything off the screen here. I'm using a different program. I'm not exactly sure of how to use all the tools yet, but we're going to keep some of this stuff. And while I'm erasing here, which is taking forever, but while I'm erasing, what I'm going to do, or what we're going to do in a second here, is we're going to look at the unit circle again. And we're going to redraw a pair of axes. There's our y-axis. There's our x-axis. Okay. And we're going to place a circle on it again. With the center being right there at the origin. There we go. And what we've already talked about, which should not be new to you guys, an angle in standard position Right there would be 0 radians. Up here, pi over 2, it's 90 degrees, right? 180 is pi radians. 3 pi over 2 down here. And we keep on going around and around. There's 2 pi, one more time, 4 pi. But what we're going to focus on is just from 0 to 2 pi. So here I need you to use your imagination a little bit in light of lack of animation, which I don't have, at least on this program. Think of this circle, okay, as a string. All right, let's say we've wrapped it around a bottle or a soda can, okay, or a paint can or something bigger than maybe. All right. And at the beginning of the string right here is 0 radians. And as you go around, the length of the string goes to pi over 2. Half of the string is pi. 3/4 of the string is 3 pi over 2 radians. And then we end up with the full length of the string at 2 pi. What I want to do is I want to stretch that string. Let's say I take it off the can or the bottle and I hold it taut. Straighten it out. Okay? And when I do that, I'm going to lay that string along the x-axis. So let me draw another pair of axes for you. Okay, so if I took that string that you just saw that was laying or made the circle and I stretched it out, right, stretched it all the way out, and its length was 0 to 2 pi, right? That means 0 would be right here at the origin, and in its fully stretched out length, here would be 2 pi. Right in the middle would be pi. Right here in the middle between pi and 2 pi would be 3 pi over 2. And right here will be pi over 2. Okay, so what I'm going to do is kind of give you a split screen view here. Let's put that XY plane back up that we just had with the circle on it. Make a little smaller version right here. Okay. And put a circle back on. Make a different color. Make it a little bigger than that. Still dealing with technological limitations on this program. I'm drawing the best I can. All right, there we go. Now remember, again, let's match these up. 0 is right here. Pi over 2 is up here, 90 degrees, you guys know that. Pi is right here, and 3 pi over 2 is right here. And of course, then you got 2 pi, and it keeps on going around. 4 pi, 6 pi, 8 pi, and so on. So what we did was we took that string that's length 2 pi, let's say, right? It's length 2 pi, and we stretched it out straight. And here's what we have when we stretch it out straight right here, okay? Now let's think about it. Let's think about it in terms of sign. In a unit circle, what we're doing is what we have is a radius of 1 unit. So think about this on an XY plane. In the middle right there is always 0, 0 in terms of X and Y, right? Well, if I go over here, 1 unit, right there, wouldn't the coordinates for that point be 1, 0? And if I went up here, 1 unit, that would be 0, 1 in terms of coordinates. What's going on? A unit, 1 unit, one unit out. If I go to the left 1 unit, the coordinates for that would be -1, 0. And finally, if I went down 1 unit on the x-axis, the coordinates for that point would be 0, -1. Now remember, every single point on the coordinate plane or the Cartesian plane has an x and a y, x and a y. X is always first, the y is always second. Remember the radius is 1 in any direction you go. Okay, the radius is 1. That's your r. In terms of the 6 trig functions, you only need x, y, and r. If you have those 3, like I've used the wording in class, you're off to the races. You can figure out all 6. So the angles we have not looked at yet are these angles that you see right here, 0 and 2 pi, that's the same angle, pi over 2, pi, and 3 pi over 2. These are known as quadrantal angles. We've looked at angles in the first quadrant right here, 30, 60, 90, or I'm sorry, 30, 60, and 45, pi over 3, pi over 6, pi over 4, and we've already started to look at the angles in the other three quadrants and refer them back to the first quadrant. Well, now let's take a look at the ones that lie, the angles that terminate right on one of the axes, the x or y axis, okay? Remember, sine is defined as y over r, okay? So, if I wanted to figure out what the sine of pi over 2 would be, I take the y value, which is 1, and the r value, which is 1, and 1 over 1 gives us a 1. So the sine of pi over 2, if I wanted to say plot these green points over here on this graph, which again, this is your y-axis right here, this is still your x-axis right here, okay? If I wanted to go pi over 2 for an input, the output would be 1. Again, pi over 2 is, or sine of pi over 2, or sine in general is defined as y over r. At the angle pi over 2, which would be a distance this far, right here, along the x-axis, okay, there's your distance right there, the y value is what the sine of pi over 2 is equal to, and it's 1 over 1, the y over the r. So what I need to place up here, I'll put a 1 right there, and I'm going to plot my point. So if I go pi over 2 over and then 1 up, I get that point plotted right there. Let's now look at pi. Again, sine. We're just doing sine right now. We'll get to cosine in a few minutes. The sine is y over r. At pi radians, the y is 0, the r is 1. Y over r, 0 over 1 is 0. So at a length of pi, okay, I go this far along the x-axis, I get an output of 0, which means I don't go up or down. So I'm going to plot a point right there. Let's now take a look at 3 pi over 2 right here. Sine is again y over r. This time the y is a negative 1, the r is always 1. Negative 1 over 1 is negative 1. So at a distance or a distance along the x-axis of 3 pi over 2, I then have to go down negative 1, because that's what negative 1 over 1 equals. So I need to place a negative 1 down here. So it's going to be 3 pi over 2 to the right and then negative 1 down. Finally, let's look at right here, 2 pi. Actually, I don't need to look, no, we will. We're going to repeat some of this, but that's okay. So forget what I was just about to say. I'm jumping ahead. I don't want to do that. So at 0 radians, or really what it is, it's 2 pi since we're making our way around, but 0 and 2 pi, 0 radians and 2 pi radians are the same. The y value is 0, the r is always 1, 0 over 1 is 0. So at 2 pi, let's place a little line here. At 2 pi, at a length of 2 pi along the x-axis, we're not going to move. We're going to stay right there. And if you remember, 2 pi and 0 radians are the same, so they both are equal to 0, so I can place a green dot right there as well. And again, it would be the same thing. 4 pi would be right on the x-axis. 6 pi right on the x-axis. 8, 10 pi, same thing. What we've done is, and what you do with any graph after you plot some points, you can play connected dots. Let's try to be as accurate as I can. Not the best drawing, but I think you get the point. What we end up with right there, folks, there's your sine curve. Okay, there's your sine curve. And now you have values for the quadrantal angles, right? You know what sine of pi over 3 and pi over 6 and pi over 4 is, because you know that from your special right triangles. Well, now you know what the sine of pi over 2 is. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2, negative 1. And sine of 2 pi, or sine of 0, is 0. And you can check that on a calculator too. Just make sure you're in radians and not degree measures. Okay? Now, this curve, I've only showed it to you from 0 to 2 pi. but it continues on like this in both directions. The same exact rotation keeps on going 2 pi in both directions. This is called one cycle of the sine curve. One cycle right here. And one cycle for the sine is 2 pi. Untransformed, that is. If you remember, we did transformations earlier in the semester. Well, these are functions just like the exponential, the logarithmic, the square, and the cubic, all those functions. We can transform those as well. So we could change the period. We could shrink or stretch. Now, we didn't do much of the shrinking and the stretching. We will for the trig functions, though. All right, we can kind of flatten it and stretch it out up and down along the y-axis as well. Okay. I think for now, if I take a look, we're only doing examples 1, 2, and 3 in section 5.3, so we're only going to look at a little bit of that. All right. But now you have the sine curve, and not only that, you have the sine of certain angles. We call those the quadrantal angles because they land right on the x or y axis. Okay. Let's do the same thing. Oh, hold on, let me see if there's anything more I want to show you here. What I also wanted to say was this is also one period. Right, the period for the sine curve is 2 pi. All right, not one period, but the period for the sine curve is 2 pi. You're going to see that the period for the cosine is going to be the same. It'll be different for the tangent. And I believe we do at least look in a general sense at the tangent curve, but we really deal mostly with the sine and the cosine curve. We really dive down deep into those. Okay? All right, so all I'm going to attempt to do, if it'll let me, is, there we go, just get rid of that sine curve. I'm going to do the same thing with these dots. Now let's take a look at cosine. Okay? Now cosine is defined as x over r, right? So if we look up here again, we'll start at pi over 2. Okay? The x value up here is 0, and again, the radius is always 1. So for cosine, it's 0 over 1, x over r, and 0 over 1 is equal to 0. So at pi over 2, we place a dot right at 0. We don't go up or down. It's equal to 0. At pi, the x value is negative 1, and the r, again, is always 1. So x over r, negative 1 over 1 is equal to a negative 1. So when we go pi distance along the x-axis, we then have to plot a point at negative 1, right below it. For 3 pi over 2, okay, down here, the x value is 0 over the r value, which is 1. 0 over 1 is 0. So 3 pi over 2, we put a dot on the 0. Okay, it's as high as it goes, or lower. It doesn't move up or down, does it? Finally, at 2 pi, which is also going to be the same as 0, we're going to put the same dot here, wherever it ends up becoming. All right, at 2 pi, we have an x value of 1 over the r, which is 1. 1 over 1 is 1. So at 2 pi, we then go up and plot a point at positive 1. And again, that's going to be the same thing as 0 radians, as well as negative 2 pi radians, as well as negative 4 pi, or 4 pi, 6 pi, 8 pi. Again, notice your period here for the cosine curve is, the period, is 2 pi. One period right here is between 0 and 2 pi. Let's play connect the dots again. And when we do that, here's the curve we end up with. It looks a little bit better than my sine curve, and I want to run out of space. There we go. Okay, so there's your cosine curve, folks. Again, the period is 2 pi. All right, now, I mentioned a few minutes ago that you do have the same kind of rules. The same rules apply for the transformations as they did for all of the other functions we did earlier. And remember, we've been building a library as we went along. We started with the squaring function, reciprocal function, cubic root, square root, absolute value. Then we added exponential and logarithm. Well, now we're adding the sine function and the cosine function to the library of parent functions. And therefore, if we have a transformation, all the rules for transformation still apply. So what I'm going to do now is look at example 1, which is on page 1 of page 420, or I'm sorry, on page 421, example 1. But before I do that, I want to explain one thing. Again, right now, what you're looking at here for the cosine curve and what you just saw for the sine curve is they're completely untransformed. All right. And I told you earlier, we're going to start taking away the theta and start using x as the angle. And the one we drew earlier was this guy, right? Sine of x. Okay. Theta, x are used in the same way. They're still angle measurements. Okay, they're still angle measurements in radians or degrees, and we're trying to stick mostly to radians for our purposes. Okay, I want to explain something known as the amplitude. I'll use a different color here. So, folks, if you look at just the cosine and the sine, if you roll back, if you go backwards in the video, you'll see it's going to be the exact same thing. How high the function goes and how low it goes. Notice it basically is oscillating between 1 and -1. Okay? The amplitude is going to be however high or low it goes from the x-axis. Okay? When it's untransformed, it's going to change. What I just said will change slightly when we start getting to further examples. You'll see what I mean. But all I want you to do is look at one cycle at the period of the sine curve or the cosine curve. Look to see how high it goes and how low it goes. Notice it's going 1 unit up and 1 unit down. Okay? And I say that in a way that kind of indicates always positive because amplitude is always going to be positive. So you'll notice in your book that it uses the absolute value symbol around the little a standing for the amplitude. So amplitude is always going to be a positive number. Now, in certain examples, that doesn't mean you can't have a negative in front. You can. Remember, a negative in front of the function indicates something that you already know about, which is a reflection of the graph over the x-axis. A negative in front of the function itself, in front of the output, in front of the y. That's a reflection over the x-axis. If you have to go back and review your rules for transformations, that's fine, but you are expected to know them by this point, and we're just applying them now to different functions, namely the sine function and the cosine function. Okay? So the amplitude for this particular one is going to be a 1. Amplitude is a 1. What you'll notice in some examples, and you're going to see it not in this first example, but in a few minutes, the a is going to be a coefficient. The a is going to be a coefficient of the function. The a is being multiplied by the cosine of x. The a is being multiplied by the sine of x. And here's where those non-rigid transformations begin to come in. Okay, we did the rigid transformations, move up, down, left, right, flip over x, flip over y. But what we didn't focus on, namely in the earlier chapters, was the stretching and the shrinking in both the horizontal and the vertical direction. Okay, well, when you have a coefficient sitting in front of the function like you do here with the a, that indicates a vertical stretch and a vertical shrink. Okay, and when it's untransformed, the way it is here, the amplitude is just 1. 1 up, 1 down. Okay, so we won't really see that until it looks like example 2. I'll show you what I mean. So let's take a look at example 1, but don't forget this, what we just talked about right here. I have one more thing to add to this, which is, if you'll notice in your book, there's a coefficient for the input. Call it a k. All right? That's going to indicate a change in the period, which is going to be a stretch horizontally along the x-axis. The a, which is the coefficient for the output, the y, the function itself, that indicates a stretch vertically, up or down. You can call it a shrink or a smush or something, flattening it out and stretching it high, making it tall and thin, if you want to look at it that way. And the k is going to be a coefficient for the input, the x. That's going to indicate a stretch or shrink in the horizontal direction. Okay, let's get to some examples. In fact, why don't we, well, I could say I could do it, but I don't know if it's going to let me delete so easily over here. And it's going to take a while to delete all these. Let me pause the video so I can delete these without you staring at me doing it for a while. Okay, still 2 little dots I couldn't erase. That's just the limitations of the program that I'm using. But let's take a look at example 1. Okay, and there's 2 parts. There's an A and a B. Sorry about that. There's part A, where it's f of x is equal to 2 plus the cosine of x. Okay. Direction C, graph. All right. Now, we haven't messed with the period yet. The period is going to, I haven't shown you yet. Remember that K is going to indicate a change in the period, most likely, or possibly. All right, so in this case, notice what we're doing to the parent function, cosine of x. We're adding 2. Whenever you add or subtract to the function itself, to the output, to the y values, that indicates a shift up or down. Okay, you're moving it up or down. This is a rigid transformation. This is the ones we did do before. So we're taking this whole cosine curve and we're moving it up 2 units. So notice if the bottom is down here at -1, if I move it up, the bottom is going to be a +1. If the top is at 1 and I move it up 2 units, it's going to be up there at 3. So that's all you got to do. You have to draw your graph accordingly, but what you have to be careful is you plot the points correctly. On the test, on the final exam, that's going to be very important. So let's draw our graph. I'm going to put the x-axis lower because we're moving this graph upwards 2 units. Get rid of that. There's our y. There's our x. Now again, this 2 being added, that's a +2 sitting right there in front of it. We're shifting the entire graph up 2 units. Again, the bottom at -1 is going to be now up at +1. And the top at +1 moves up 2 units. It's going to be up there at 3. And the one thing I didn't mention, notice right here, these 2 points, which sit at 0, they're also moving up 2 units. They're going to be at 2. Now, the period hasn't changed. It's still going to be 0. Oh, I don't know why it's doing that. Hold on. Okay, let's see if I can try it again. The period is going to be 0 to 2 pi. Hold on, folks. Okay, I just must have been some kind of glitch. Again, the period is going to be 0 to 2 pi. So there's your pi. Right here is your 2 pi. In between is 3 pi over 2. And right here is pi over 2. Okay, so everything is moving up 2 units, straight up. So right here at 1, that moves up to 3. That's the point. Right here at pi over 2, which is at 0, is going to move up to 2. 0 up to 2. That's the point. Then at pi, it's going to move from -1 up to 1. Ignore that little green line. That's one I couldn't get rid of. Draw our dot there, our point. 3 pi over 2 is going to go from 0 up to 2. And finally, 2 pi goes from 1 up to 3. Everything moves in a rigid fashion up 2 units. And then we draw our graph. Better than you can, maybe with a computer pen. Okay, and there's your cosine curve. Let's look at example B. Again, I'm gonna erase these, but the thing is, you can rewind and pause the video, which is a very big help. All right, let me erase this. The little dots are tougher to erase. Get rid of them. Oh, there goes that one away. I just had to go ahead and delete the whole screen. It's again, limitations for some of these these programs. They are what they are. Okay. So the next example, part B, looks like this. You got g of x is equal to negative cosine x. So you have to remember what the negative means. That means you're reflecting your graph over the x-axis. Really got to press these buttons down hard to make them work. Give me a vertical line. There we go. So remember, when you reflect over the x-axis, folks, everything that's above goes below. Everything that's below goes above. Let's label our graph. There's pi. There's 2 pi. That hasn't changed. 3 pi over 2. The period is still 2 pi. We is flipping. Now, I had to erase it, but for the cosine, again, didn't we start right here? So if this point is where we start, when we reflect it, we start down at -1. Okay? And then at pi/2, it was staying right there at 0. That's not going to change. For pi, remember we had a point down here at -1? Well, now the point's going to be up here at 1 since we're reflecting over the x-axis. 3pi/2 stays at 0. And finally, 2 pi finishes down here. And if you think back to when you reflect your parabola over the x-axis, right? Everything, it goes from a U upright to an upside down U. Well, the cosine curve, is kind of a U shape, right? That's pretty much what happens with the cosine. Flips upside down. And you want to try to draw it smoother than I'm drawing. There should be no straight lines on here. I'm just trying to, it's again a limitation that I'm going with the best I can. All right. So there's the graph for example 1A and B. Now let's take a look at example 2. And this one's pretty straightforward in terms of what it's asking us to do. It simply says find the amplitude. All right, find the amplitude of this function right here, and it also wants us to sketch the graph. Now, as I write it, notice what the A is, folks. The A is the coefficient of the function, the number that's being multiplied against the function, against the output, against the y. It's right there. And remember, amplitude is always absolute value. So if you take the absolute value of -3, you get an amplitude of 3. Now, that negative still has a function. Remember, just like in the very last example we did, example 1b, the negative indicates when it's in front of the function, as it is here again. And then, in fact, that last example, it was in front of a 1. It was a -1. This time it's a -3. That negative indicates a reflection over the over the x-axis. Okay? So let's draw our axes real quick. Let's get my straight lines to work. It's sloppy, but for some reason, again, it's the program, folks. Again, our period hasn't changed. It's still pi. It's still 2 pi here, 3 pi/2. And I want you to take special note of these 4 locations that we've been talking about, because when it comes to your test, your final exam, and even your quiz, and probably on the web assignment as well, you have to be accurate with where you're locating these points. Now, here's where you can get a little creative, not lazy, but instead of putting a 1 here, since the amplitude is 3, that means the graph is going to go up 3, and it's going to go down 3. As long as your graph is labeled correctly, then there's no problem. Again, it's flipping over the x-axis, right? So it looks just like the last one. The only difference between this example and the last example we did is that the amplitude is no longer a 1, it's a 3. So you'll notice in the end, the graph looks exactly the same, doesn't it? However, I labeled it differently. Try to get it right through your points if you can. Okay? I just labeled it different. In the last one, this was a 1 and a -1. There's the difference. That's the only difference between this graph and the last one. Okay? One more example, and this is where the stretching of the period is going to, or I should say a changing of the period is going to come into play. Let me erase this off the screen. Again, you can rewind it and go back and pause it. And play it again and again and again. Example 3 has 2 parts. Part A wants us to find the amplitude and the period. Now, to find the amplitude, you should know by now, you should be thinking it's quite easy. Simply look at the coefficient of the function. Obviously, for this one, the amplitude is going to be a +4. 4 up, 4 down. Okay? Here's your k. If you roll back, remember I had a k sitting in front of the input as a coefficient for the input, the x value. When you multiply the x value by some coefficient other than 1, okay, now we're going to have a change in the period for both the sine and the cosine. Since the period is 2 pi, we're going to use that k value to figure out the new period. Let's say the period is going to be changing. All you do is take 2 pi and divide it by k. Whatever the k is, whatever the coefficient is in front of the x. And once we have the amplitude, which we can clearly see is a 4, then we know how high and how low to label the tops and bottoms of our cosine and sine curve, in this case the cosine. The 3 is going to be used to figure out the period. Plug it in, that's the k. The coefficient of the input x is the period. So for this one, when you plug in a 3, you end up with 2 pi over 3. What that means is, on the previous examples we did, the period was 2k, because what was sitting in front of the x in all 3 of those examples we just did was a positive 1, and 2k divided by 1 is still 2k. When it's something other than 1, as you can see right here, it's going to change. So if the period is how far it takes one sine curve, or one cycle of the sine curve, or one cycle of the cosine curve to be drawn out, now we're going to stretch our sine, in this case the cosine curve, from 0 to 2 pi over 3. Something else I want you to notice, folks, basically when I did 0 to 2 pi, didn't I break down everything pretty much into quarters, right? I put pi right there, and I put 2 pi right there, and 3 pi over 2 right there, and then pi over 2 right there. Notice it's 4 equal parts. Each one was at pi over 2. Half a pi, half a pi, half a pi, half a pi to give you the full 2 pi. Well, what you're doing for this one is we're going to stretch it out from 0 to 2/3 of a pi. So you got to be a little bit clever here. And this is where I know people go crazy because it's fractions. Well, like I said before, folks, fractions, let me get rid of that. Fractions have not changed. You just have to get used to them. Okay? So here is 2 pi over 3. That's as far as we're going to stretch it. And this is still 0 radians right there. What you need to do is figure out, well, what is half of 2 pi over 3? If I took 2/3 of a pi and I cut it in half, what would be the middle point? Now half of that one isn't too bad, right? If you got 2/3, then half of that would be 1/3, wouldn't it? So that goes right here in the middle. All you need now is to figure out what the quarter points would be. So again, try to think about it and make it as easy as you can for yourself. If this was 2 pi over 6, doesn't look like a 3, does it? But if that were 2 pi over 6, you would agree with me that 2 pi over 6 and 1 pi over 3 are the same thing. Pretend for a second that it is 2 pi over 6. What would half of 2 pi over 6 be? Wouldn't it be 1 pi over 6? So basically, I went from 2 pi over 6 backwards to 1 pi over 6. If I went frontwards, wouldn't it be 3 pi over 6 right here? And isn't 3 pi over 6 the same thing as pi over 2? Okay. Now, if you labeled it or left it as 3 pi over 6, would there be a problem? I don't want to say there wouldn't be, but you should always try to reduce fractions that you use to lowest terms. I'm deliberately not going to use 2 pi over 6 because that's really equal to 1/3 pi, okay? I'm not going to use 3 pi over 6 because that's really equal to pi over 2. 4 pi over 6 would be right here. If I reduce it, it's 2/3. But either way, you got to get these fractions down. You got to, whatever your period is, folks, take note of this. Write it down somewhere. Whatever your period is, break it up into 4 equal parts and label each interval correctly. We know the amplitude goes up 4 and down 4. I don't need to write 4 units in, like 1, 2, 3, 4. Just write 1 unit and label them both with 4 and -4. Okay? There's no flipping going on in this particular case. We didn't reflect over either axis or anything like that. So I'm going to draw my dots. We start at 4. We come down to 0, down to -4, up to 0, and then back to +4. And then we play connect the dots. We've given the amplitude of 4. We've given them the period of 2 pi over 3. And then we used both of those and our knowledge of what the cosine curve looks like and any other knowledge of transformations or lack thereof, meaning no negatives in this one. And we can then graph it, and that's what it wants there. Last example is example B. So we have this other example here, y equals -2 sine 1/2 x. So let's break this down, folks. Notice the form it's in. And notice the important information that we can draw from this. In fact, maybe this will help. Let me do this. Just so they stand out a little bit more. The A and the K. I'll put them in black. So over here, notice what your A is. It's a -2, but amplitude, which is what the A is for, the amplitude, how high and how low your sine curve, in this case, will go, is the absolute value of -2, which is a 2. Now keep in mind that negative is still going to have a role. Okay, that negative in front of the function indicates that the graph is going to reflect over the x-axis. Okay, so our amplitude is a +2. That means our graph is going to go up 2, down 2. All right. This value, that's the coefficient for the input, the x. Again, the 2 or the -2 is the coefficient for the whole function. The whole function is f of x, right? And f of x is y, the output. This 1/2 is the coefficient for the x, the input. That indicates or has a role to play in figuring out what the period will be, which is how long your single cycle of your sine curve is going to stretch along the x-axis. So remember, it's not just 1/2. You don't look at that and say, oh yeah, the period is 1/2. No, the period uses this k value. Again, one more time, we had it on previous, on the board here previously. It's 2 pi for sine and cosine divided by k. In this case, it's 2 pi divided by 1/2. Okay, so 2 into half, or I should say a half into 2, you can fit 4 of those, can't you? I don't know if you can see this, if it's off the screen or not. I think you guys can still see it. All right, let me put it down here. All right, 2 pi divided by a half. How many halves can you fit into 2? You can fit 4 of them. Okay, so the period is 4 pi for this particular one. Amplitude is 2. Period is 4 pi. So now we have enough information, along with that negative, we have enough information to graph this guy. It's going to go as high as 2 and as low as -2. Okay? But again, the key part that you have to make sure you take care of, get this right. The buttons are not very good here. The part you're going to have to take care of is making sure that you break the x-axis out into 4 equal parts. Remember, we did half pi, 3/2 pi, and then 2 pi. All right, this time the period isn't 2 pi, the period is 4 pi. So we're going to stretch it from 0 all the way out to 4 pi. And this one's a little bit easier to calibrate, isn't it? Right there in the middle is 2 pi. In the middle here is 1 pi. In the middle here is 3 pi. You gotta have the, for the sake of the test, the final exam, and the quiz, you gotta have these labeled, folks. You gotta have them labeled. Remember, it's gonna go as high as 2. And that's good enough right there. Make sure it's even length down here. Most likely, it'll, you know, the axes will already be printed for you on the quiz and definitely the test. You might have to draw it with your ID card on the quiz. We'll see. The graph will go as high as 2 and as low as -2. Now you know what the sine curve looks like, but remember, it's reflecting over the x-axis. So follow the cursor. This is what it would normally look like, all right? This is the sine curve without the reflection. We're going to reflect that back over the x-axis, which means instead of starting or going from 0 up to 2, it's going to go from 0 down to -2 at pi. So let's draw our green dots again. I'm going to start right here. And again, it's going down. So at pi, it's at -2. Comes back up. At 2 pi, it's back at 0. Back up at 3 pi, it's at 2. And then finally, it finishes right here at 0 for 4 pi. And then we go ahead and we sketch it in. Notice the sine curve, not only is it reflected over the x-axis, it's also stretched, one complete cycle is stretched over a period of 4 pi. Okay? All right, so that's everything we need to cover for section 5.3. And the video is about as long as I expected it to be, close to an hour. But again, you have the ability to look over this video over and over and over again and use it to your advantage as much and as often as you can between now and the final exam. All right. I'll send an email. You'll have an email that is posted on Canvas once it's ready. See you guys in class. Take care.